do you ever see any y? Or in the y, is there any x's? And the answer is no. The x and the y are independent of each other. Okay. So x and y components are independent of each other. Well, if these are independent of each other, then aren't we just solving two different problems? And the answer is no. Yes, there is no y's in the x and there is no x in the y's, but what do you see in common on both sides?
Acceleration, velocity, and time?
Okay, well, they have subscripts, that's true, but I was talking about very precisely notated ideas. Although they do, the accelerations have x's, same with the velocities and the positions. But what shows up on both sides?
Both functions of
Time! Time! Time is how these two equations communicate with each other. So these are unified but by time. So but are unified by the universal parameter time. So often you're going to want to know something from here. This is going to be the heart of the problem. You want to know something like, the x position. But you're going to have to use the y information to get the time so that you can find out where the x position is at that corresponding time. So these are going to be communicating back and forth through time. So in these types of problems, at minimum, it will be a two-step problem. You guys remember that multiple step problems that I was mentioning? The easiest one I can make, the one that's actually possible, is a two-stepper. Because you always need to get time first, and then the second step, you might be able to get your answer. But of course, there might be a few individual steps before you can even get to time. And also a few steps after you get the time as well. Oh, yeah. So that's two-dimensional motion in general. Just like how we did in one dimension, we looked at a few specific types of motion like free fall and inclined plane. We're going to divvy up the two-dimensional motion into a few different types as well. The first one is what is called projectile motion. Projectile motion. Let's first define what a projectile is. It is an object moving in 2D under the influence of gravity. Now, one of the things in common you guys should see with free fall, with inclined plane, and with projectile motion is the keyword of gravity. When you have gravity, you typically do have the constant acceleration condition met, meaning these equations are applicable. If you don't have constant acceleration, throw these equations out because you can't use them. So it must be a constant acceleration problem for this to be accessible. Now, one of the characteristics of a projectile motion is that it has a parabolic trajectory. So parabolic trajectory. Meaning, if we have our x and y plane, and let's say we drop the tennis ball, it will look something like this. And you have a upside down parabola repeating over and over again. And after each successive bounce, the next one is slightly smaller. So this would happen if we were to drop a tennis ball. So this is a qualitative characteristic, but we're trying to do it in a quantitative fashion. Quantitatively, what is projectile motion? So the key quantitative characterizations are these. First is acceleration in the y direction. Because it's under the influence of gravity, acceleration in the y direction is simply going to be negative g. When have we seen this before? Free fall. Projectile motion in the y direction is simply free fall. An object is in free fall because indeed gravity is working on it. Acceleration on the x direction is going to be equal to 0. So in the x direction, there is no acceleration. One of the implications of this is that Vx is constant. If there is no acceleration, then the velocity in the x direction is constant. This is married to projectile motion. As soon as you see projectile motion, you should know the two different values of acceleration. Those go hand in hand. Projectile motion, boom, you know these two. So one thing we're doing here is assume negligible air resistance. Assume negligible air resistance. Because by definition, a projectile is only under the influence of gravity. We know acceleration has gravity and there's no other thing affecting it, so the acceleration is going to be 0. Now, one thing to note, let's come back to our set of equations, the most important things in this section. Acceleration, velocity, and position. So all of these three. They not only have time in common, but there is something that everything has in common. What is it? Yes, everything uses initial values. So, initial condition, do you guys see here? Initial acceleration, initial velocity, initial acceleration, initial position, initial velocity. I forgot the knots there. It's initial acceleration. This is initial acceleration. On the y, you have initial acceleration, initial velocity, initial acceleration, initial position, initial velocity, initial acceleration. You guys see that? The initials are everywhere, meaning initial conditions determine everything. Initial conditions determine everything. So, where do you get the initial conditions? where is the heart of the problem in all of this? It's going to be, did you read the problem correctly? Because where do you get the initial? In the problem. That's it. After that, you're just mixing and matching these set of equations. That is it. At least in this section, that is it. So let's work on a few different, just one initial but very common scenario that you're going to see. Often you're going to be given things like the launch angle, theta, as well as the launch speed. It's called V naught. So when you plug both of these together, you're going to get velocity is going to be V naught and theta. Which form is this vector notation that, it's in vector form, right? The information that's going to be provided is often going to be in the vector form, which is the less useful form. This is vector form. But in terms of using this information, we need component form. How do we do that? How do we go from here to the component form? This is like week 1 stuff. Maybe it's week 2 stuff.
Use Pythagoras.
Not Pythagoras, but SOHCAHTOA. Because we know the theta, that is going to be V naught, and the theta is made with respect to the horizontal. What shape do we have? What kind of a triangle?
Right triangle.
Yeah, right triangle. So V naught x, by the trigonometry of this, is going to be V naught cosine of theta. And V naught y is going to be V naught sine of theta. And it is here, this is the reason why we're going to be using trigonometry over and over and over again. And I don't recommend you actually memorize, V naught x is always V naught cosine of theta, because that is not true. You should always get used to just drawing this out yourself to see the true relationship and actually using the SOHCAHTOA. So, then your velocity is actually going to be, or initial velocity is V naught cosine of theta I plus V naught sine of theta j. The initial conditions determine everything, meaning you gotta know how to do this to that if you even want to have a chance at getting this solution correct. Because as soon as your starting point is wrong, everything else is going to be wrong. On top of this graph, let me actually show what the trajectory would look like, because I see so many incorrectly drawn trajectories. If this is our x and y coordinate system, the trajectory does not look like this.